Welcome to the IAS seminar series on big data. And today, it's my great pleasure to introduce Professor Michael Franklin of UC Berkeley. Michael is the Thomas M. Siebel Professor of Computer Science and has bravely taken up the chair position of Computer Science Division at Berkeley since July this year. He is also the director of the Algorithms, Machines, and People Laboratory, AMPLab. This lab is a long-term collaborative effort at UC Berkeley involving students, researchers, and faculty from a wide range of the computer science and data-intensive application domains to address the big data analytics problem. It currently works with more than 20 industrial sponsors, including the founding sponsors such as Amazon Web Services, Google, and SAP. It has received a U.S. National Science Foundation SAIS Expeditions in Computing Award and was announced as part of the White House Big Data Research Initiative in March 2012. Mike is a versatile expert in the database, data analytics, and data management fields as a researcher, lab director, faculty member, entrepreneur, and a software developer. He is well known for his pioneering work in distributed information management. One of his early projects that he created while a faculty member at the University of Maryland was called DIMSUM, standing for Distributed Information Management Systems at the University of Maryland. Techniques proposed from that project influenced the field profoundly, such as query scrambling, X-join, and semantic caching. Many PhD students, including myself, were inspired by his work. He was awarded Fellow of the ACM, Association of Computing Machinery, in 2005 for contributions to distributed information management. Over the years, from his PhD at the University of UC Berkeley and to his faculty stint at the University of Maryland and his tenure at the UC Berkeley, he has participated and led a number of highly impactful projects, such as the Shore Storage Manager, the TinyDB Sensor Network Query Processor, the Hi-Fi Distributed Stream Processor, the CrowdDB Crowdsourced Query Processor, and the current AMPLab. His research papers have won 2 of the Test of Time Awards at the ACM Sigma conference. This is the major conference in the database field. Moreover, software systems and techniques produced from these papers have been used and applied in various commercial products and real systems. His current work on the AMPLab has already made a big impact to both research and practice. I'm sure he will tell us a lot of interesting and exciting stuff about the project today. Without further ado, let's welcome Professor Michael Franklin.
Wow, okay, well, thank you. That was, I think, the best introduction I've ever gotten. So I appreciate it. She forgot to mention that I spent part of my time in my sabbatical in 2003 here at Hong Kong UST, so it's good to be back. So what I want to do today is kind of give you an overview of the project that we've been doing at Berkeley for the last few years called the AMPLab, and in particular, the software that we've been building in the AMPLab that we call the Berkeley Data Analytics Stack. And it's a little bit of a I'm trying to cover a lot of ground in the talk, which means I probably won't cover any of it really well. But what I really want to do is a few things. I want to tell you about the system we've built and what's interesting about it. But I also want to address a few sort of meta issues. One is sort of just tell you a little bit about how we've organized the lab and how we've been able to build a real impactful system really built largely, almost exclusively by graduate students that's had real impact in the industry because there's been some, a lot of changes in the way the industry is working that's made that a lot easier than it used to be. And then also, I want to talk a little bit about big data and data science and what all that stuff means, just because there's a lot of excitement around it. There's also a lot of skepticism in terms of, what's really there, what are the research issues, and so on. So kind of a big agenda. We'll see how much of it I get through, but why don't we just jump in? So this is just kind of a snapshot of a bunch of news articles written over the past couple of years about some of the software that we've been building in the AMPLab. You might have heard of a system called Spark. That's what I'll be talking a lot about today. It's now called Apache Spark because we donated it to the Apache Foundation. But there's a whole set of analytics software that we've built that as we've been releasing it, it's been adopted in various ways by people in industry. And so this is just some of the press we've gotten on that. This is an article I actually found on the flight over here, where this is a Google Trends graph, right? So it's just a scaled. That's why there's no lines on the y-axis, but it's just a scaled representation of the frequency of searches for different terms. And the red is Apache Hadoop, which hopefully, since you're here for a big data talk, you've at least heard of, right? That's sort of the default computational engine that people are using for big data. That's the red, and that started, around 2008 and went up from there. The blue is our system, Apache Spark, which we released in 2010, but nobody noticed. But very recently people started noticing, and what this article was about is that finally, last month or something, those lines crossed. So there's actually more people on Google searching for Apache Spark than are searching for Apache Hadoop. So whether that means anything or not, it just gives you some feel for what we've been able to do. Okay, so I think I actually told you what I want to do. I want to talk about big data, what that means a little bit, to talk about the software we've built, and then I want to kind of jump up a level and tell you about how we organize our research, because there's some interesting things in there, and then kind of just wrap up with some thoughts on what's next and where things are going. So go through this quickly, but why are people so excited about big data? There's a lot of reasons. Some of them are more justified than others, but the thing that's true for sure is that just about everything we do is becoming data-driven. And so this is just a sampling of areas that are just generating huge amounts of data. So the one that's probably the most obvious to computer scientists is this one here, where it's just as more and more activities move online, there's just more and more data being generated about those activities. And what you might not, I think probably most of you realize it now, but when you do something as simple as like clicking on a link on a web page, or even worse, clicking on an advertisement, that sets off this whole cascade, right? The site you're visiting will record the fact that you did that. But more than that, sites that you don't even know exist are recording the fact that you did that. And recording a bunch of things underneath in terms of the systems that are serving up that data, the underlying back-end systems that are maybe generating the transactions that resulted from you clicking on that link and so on. And so one little activity online just generates this flood of information, okay? And so, and that's not going away, it's just increasing, right? So mobile devices and so on. Another place where a lot of data is coming from, although not nearly the same amount of volume, is user-generated content, but it's valuable in its own way. So, people tweeting, posting things on social networks, and so on. Internet of Things, or machine-to-machine communication, is obviously another area where increasing amounts of data are being generated. And then finally, this one I'll just mention, especially those of us at universities, this is really important, is that basically all areas of science are becoming data-driven. So this is a graph. It might be a little hard for you to see, but it's over time. It's on a log scale. This kind of boring straight line, that's Moore's law, right? That's the thing that us computer scientists are, so proud of, right? That every 18 months things get twice as fast, or twice as cheap, or twice as dense, whatever you like to measure. This line here is a cost of sequencing genomes, okay? And the one thing you'll notice is that is dropping, much, much, much faster than Moore's law. So if you're doing genomics work, basically your computers are getting slower and slower every year relative to the amount of data that you have to deal with. Okay, and this is happening across, any field you can think about, whether it's astronomy or physics or social sciences or whatever. Just everyone's seeing this huge explosion in the amount of data. So one reason people are so excited about big data is it's just everywhere. Okay, and there aren't really any signs right now that it's going to slow down. Okay, so let's try to tease apart a little bit about what this term big data means, right? Because it's a little bit of an unfortunate term. People get hung up on the word big. Okay, and so this is one definition that I really don't like, which says, well, it's data sets that contain billions or trillions of records. Okay, and that's an obvious translation of big, right? But it's not a very useful one, right? So, there's a couple things that are wrong with this definition, right? One of the most obvious ones is, well, if you have 1 billion minus 1 records in your database, does that mean it's not big data? Right? It's kind of crazy. And furthermore, in 10 years, this is going to look silly, right? Oh, you only have 1 trillion records? That's nothing, right? So, it's just not a scalable definition in either direction. Okay, so there's got to be more to it than that. So the other thing I don't like about this is that it defines big data as a problem. Okay, I've got all this data and somehow I have to do something with it, right? This is terrible. Okay, well, I'm a database person. I love having data, right? So I'd like a definition that doesn't define data as being a problem. So here's a kind of something that's heading towards a better definition that I found was useful. So it was from a pamphlet from the O'Reilly group, which is one of the groups that's really been out in front of the data science and big data movement. And basically what this quote says is it's about a breast cancer treatment. And it says that for a long time we thought this treatment was roughly 80% effective for patients. But now we know a lot more than that. We know that it's 100% effective in about 80% of the patients and completely worthless in the rest. And the trick is, right, that's kind of a funny definition. It's kind of a funny statement, right? Because in some sense it looks like maybe it's saying the same thing. But it's not, because the difference between the top statement and the bottom statement is that if you can collect enough fine-grained data, you can actually figure out who's in that 80%. Okay? So you can so it's not a random, it's not a roll of the dice whether this thing's going to work or not. You figure out who are the people that this drug works for, and you give them the drug. And for the other people that it's not going to work for, you try to, you find some other solution. And so, where this comes from is from the way sort of clinical trials have traditionally been done, right? If you were doing 80% is a good number. But if you were doing a clinical trial and your results showed you that that the drug you're testing is effective in 1% of the cases, you'd throw it away. You'd say this thing's completely worthless. But if you could figure out exactly who that 1% is, you could save a lot of lives that way, right? So it's all about being able to collect enough detailed information. And so the idea of big data, to my mind, is that there's a certain tipping point, right? That you're collecting data, either more data about more individuals, or finer grained data, right? So over smaller and smaller time intervals, or maybe wider data, right? So you're collecting more features and more dimensions. But at some point, you get to see things that you wouldn't get to see if you didn't have all that data. Okay, and so that to me is what big data is about, that there are certain phenomena, certain things you can discover only when you've collected enough information of the right type. Okay, and that's basically saying that big data is an opportunity. So if we can figure out how to make sense of these increasing amounts of information we're getting, we can solve problems that we wouldn't be able to solve if we didn't have that data. That to me as a researcher is a much more interesting situation to be in. Okay, so big data as an opportunity. So, here's another way of thinking about it. This is an application we built in our lab. It's called Carrot. And what Carrot does is it runs on your smartphone, and it watches what applications you're running and what's happening to the battery on your device. And periodically, it uploads that information to an application that we're running in the cloud. Okay? Now, when you run Carrot with 50 phones, which is the way we tested it, you basically learn nothing. There's nothing interesting there. Okay? But Carrot's been downloaded, this is an old slide, it's been downloaded about 1 million times. Okay, now when you can collect data from 1 million different phones, you can start to build models about for a particular phone, running a particular version of an operating system, which applications are correlated with heavy battery usage and which ones aren't. So that way, you can collect that information. You can then report back to each individual phone, hey, here are things that you're running on your phone that everybody who has your phone, it drains their battery, okay? So we can make predictions. In fact, if you stopped running this application Pandora, we'd expect your battery would last an extra hour and 27 minutes. And we know that because we looked at all the people who have your phone that weren't running Pandora, okay? So that's, again, if you didn't have enough data, you wouldn't be able to figure that out. The other thing we can do is we could say, hey, whenever you run Google Maps, your battery drains really quickly, but most people with your phone, they don't have that problem. So maybe you need to reinstall Google Maps, right? So you can do both. You can find the patterns and you can find the outliers, okay? And so, this is kind of, maybe you might think of kind of a simple problem of how long is the battery going to last on your phone? But imagine if this was a medical application where you're trying to come up with a precision prescription for an individual with a particular problem, right? So that's, again, sort of the power of having a lot of data. Okay, so we talked about this. So we, a bunch of us at Berkeley got excited about big data. Actually, before it was, well, it doesn't matter. But it wasn't really called big data. When we started looking at it, was probably about 2009 that we started working on this. But we got a big boost when we got this award for. So the White House, the U.S. president, decided that big data was going to be important. Started this big initiative, and we were lucky to be able to be part of the projects they announced when they funded that first part of the initiative. So what are we doing? It was actually in that quote, but what our approach is we basically said there are three classes of resources that you have available to make sense of big data. Algorithms, right? So think about machine learning, statistical processing, and so on. Machines, cloud computing, scalable clusters, warehouse scale computing, and so on. And then the P is people. So you can think about people that are interacting with the data, like analysts and data scientists, or kind of, from my point of view, kind of more interestingly, you can think about using the crowd to find data for you, to clean the data, to help answer the questions that the algorithms and the machines can't quite do yet. Okay? And the idea of our project is to say, all right, we have these three very different types of resources. How do we put them together into a single system to solve a given data-driven problem, okay, or to answer a certain question? So that was kind of what we set out to do. Okay, so now I want to focus more on this analytics stack that we've built. And to understand what we've done, it's interesting to kind of look back a few years. So a lot of the excitement in what people are calling now, the big data ecosystem, started because a number of big web companies realized that they were going to be faced with these huge amounts of data. And they felt that either the existing solutions, like existing database systems, couldn't scale to handle those data volumes, or even if they could scale that big, they were going to be too expensive. So they started implementing their own systems to process large amounts of data. And so, this is companies like Google, Yahoo, Amazon, and so on. And the thing that really caught on, or caught people's attention, was a system called MapReduce, which was developed at Google, and basically lets you write at a pretty low level programs that are highly parallel. So as you get more and more data, you can add more and more machines, and you can still process, you can still keep up with the data volumes. What really caused this to take off is that people that were at Google and places like that were used to this type of technology left, right? They went on to other companies, and they realized that they needed those types of tools. And in particular, there was a group that built Hadoop, which we've already mentioned, which is basically an open source version of MapReduce. So MapReduce, initially you had to be at one of these companies to get access to this technology, but once it was put into the open source, everybody could get there. So a lot of people got excited about MapReduce, and they said, hey, this is great. I can now run scalable computing, right, which is something they couldn't do before, especially they couldn't do it with free software. And they said, it's great, except that, I've got a special problem, right? I don't have, I'm not doing this generic, computing PageRank or whatever that, that Google was doing. I'm working with stream data, or I'm running SQL queries, or I'm working with graph data. And for each of these problems, somebody said, okay, I'm going to take this MapReduce idea, this ability to spread computation across all these different machines, I'm going to specialize it. So I'm going to build a version of the system that runs SQL. Okay, it doesn't do anything else, it runs SQL. Or I'm going to build a version of the system that lets me run graph algorithms over it. Okay, can't do anything else, but it'll do graph algorithms, and so on. Okay, so there was this explosion of different systems that all solved some specific problem. But the problem here is if you wanted to solve kind of an end-to-end data problem, you'd often have to use a bunch of these things. And they weren't built to work together. Okay? And so what you end up doing is having to learn a bunch of different systems, having to keep track, right? These things are all open source, they're changing constantly. So you have to keep track of all these different systems. And then when you want to move from one set of processing to another, typically what you had to do was take the data, copy it out of the system that you had it running in, and load it into another system. Okay, and then copy it out and load it into another system, which for big data is basically the worst thing you can do, right? Because you don't want to have to move that stuff, and you certainly don't want to have to convert it. Okay, so this is kind of the state of the art in the big data ecosystem. So what we did is we came at it from a different way. We said, all right, we like MapReduce too, but why don't we try to do something else? And instead of specializing MapReduce for every problem, let's try to generalize it. Let's try to make it bigger. Okay? And it turns out that there are two additions that you need to make to Hadoop to make it much more general. One is you have to have more than map and reduce, right? So MapReduce is called that because there are two things you can do to data. Map is apply some function to individual records. Reduce is take a collection of records and smash them together. Okay, that's map and reduce. You want to do more than that, okay? And so you want other operations, okay? And you want other patterns. And the second thing is between each of those operations, you want to be able to share the data. So you don't want to have to, write the data out to disk and then read it back in, okay? And what we found was just with these two extensions, you can implement SQL, you can implement streaming, you can implement graphs, you can implement machine learning libraries, okay? And obviously, there's a lot of benefits to this, right? If you're a user, you don't have to learn a bunch of different disparate systems. You don't have to track them all. You don't have to worry about which pieces to put together. And if you're doing an operation that requires a few of these different things, you don't have to move the data from system to system, as we talked about. All right? So we built a system called Spark, which is basically our substrate, on top of which we built the rest of the stack, which is all these other types of functions. All right, and so what I want to talk to you about is kind of the overall structure, and I'll spend more time on Spark just so you see what we did there. Okay, but that was the basic idea. Instead of building an individual implementation of something that looks like MapReduce to handle every access pattern I could think of, let's try to generalize that lowest level and be able to build all our different interfaces on top of that. So we can have a unified system. Okay, so that's what we did. We built this thing called the Berkeley Data Analytics Stack. The acronym is BDAS, and we pronounce it badass. And, and this is what it looks like. And you kind of have to read this from the bottom up. So at the lowest level, we do resource virtualization. And there's two systems there. One we built, one we didn't. So the legend here is the blue things are things that we've built in the lab, and the gray are things that were built elsewhere, but that we work well with. So at the lowest level, you want to be able to take a huge room of machines and split it into individual clusters virtually so that you can share it among different users and have different instances of the systems running and so on. So we built a system called Mesos in the lab, and eventually that got released as an Apache project. There was a Another project that came along later called Yarn that got quite popular, so we play with Yarn as well. Okay, but that's at the lowest level. Just take physical machines and virtualize them, basically. The storage layer, we use existing systems again, so we're big fans of the Hadoop file system, which is a wonderful scalable file system. You basically just add more disks and throw more data at it, and it just grows and grows and grows. And so there are people with HDFS implementations with many petabytes of data sitting on them, which is a scale that you really just didn't see before. Most people didn't see before. And we built on top of that an in-memory caching layer called Tachyon. Okay? And underneath Tachyon, we can have different file systems. So, the Amazon file system, I don't have the whole list here. There's a system called Gluster. Ceph is another one that's used in scientific applications. There's a whole bunch of file systems that sit under Tachyon. And then the fun really starts up here. So our main processing engine, which we're going to talk about, is Spark. And as I mentioned, that's now an Apache project that you saw. I was showing you the popularity of it. I'm not going to talk about this today, but ask me questions. I can try to answer them. But Spark was meant to solve analytics problems, so kind of batch analytics mostly. Velox is meant for serving. So Spark applications tend to work. You get data, and then more data comes in, and you process it, but you don't really touch the old data. Velox is meant for data that's constantly being updated, so it's a little more transactional. Okay, and this is a new part of the system we're building. And then, the real action is up here. So we have a bunch of different ways of getting at the data. There's a streaming engine. There's a query processor. There's a graph system I'll tell you about. There's a library of machine learning functions. There's an approximate query processor. There's a human crowdsourced data cleaning module. There's a declarative machine learning system, so you don't have to say exactly how to implement your machine learning, but just sort of at a high level what you want to do. And then there's even an implementation of the R statistical language that runs on top of Spark. And then on top of that, we have a bunch of applications that we've built that I'll tell you about. Some I actually already told you about the one for cell phone battery debugging. But we're doing stuff in Internet of Things, and we've done some stuff in genomics. I'll tell you a little bit about that. But this is what we've managed to build in the lab. And some parts of it are more baked than others. But Mesos is out of the lab, and there's companies around it, and lots of people using it. Spark is largely out of the lab now. And again, there's companies. I'll show you some of the traction that we've had there. And then, a bunch of these other components are in various stages of alpha and beta release, and some of them have been baked into Spark. Okay, but that's kind of the view of our system. So, what I want to do is talk a little bit about Spark, because that's kind of the heart of the system. All right. Oh, and I'm going to do that twice. All right. So. I showed you that curve at the beginning of the interest that sort of happened in Spark over the last year. There's a bunch of reasons for that. Not all of them are technical, but I love this quote here that just says it's only September. Right? I found this in September, but it's pretty clear that 2014 is going to be the year of Apache Spark, and Apache Spark goes back to this paper that we wrote for a workshop. Back in 2010, where we laid out the architecture of Spark. So basically from 2010 as a workshop paper to 2014 as basically being a big deal in industry is about as fast as things go in terms of technology transfer. And I want to talk a little bit about how that happened, a little later. Okay, but what is it? So Spark came from a very interesting place. We had a lab that was basically a combination of computer systems people and machine learning people. And the machine learning people were trying to run some algorithms on Hadoop, and we're just getting terrible performance. And started talking to some of the students who worked on systems and said, hey, can you help us debug this? What are we doing wrong? System students looked into it and said, no, you know what? You're not doing anything wrong. The problem is that the application you're trying to run, this algorithm you're trying to run, just isn't the kind of thing that Hadoop was meant for. And in particular, what they were trying to run was an iterative algorithm that basically goes over the data multiple times before it computes its answer. And so the way this looks in MapReduce is you start off with an initial model, you read in your training data, and then you apply a function to each individual record, and then you can combine the results, and then you basically learn a new model. Okay, and so you come out with a new model. Then you go through and you iterate. You take the new model, you apply it to the training data, right? Map, reduce, you come up with a new model again. And you keep going, okay? Now, why was this a problem for Hadoop? I hope I'm going to show you. Okay, well, it was sort of on there. So let me go back. So the problem is that the way Hadoop was working was that it basically, for each iteration, it would read things in from disk, it would process it, it would write things out from disk, and then when you would iterate again, it would start as if it was a completely new program. It would read the training data in from disk again, it would write stuff out to disk again, and you'd keep doing that. And so you basically, each iteration is communicating through the disk, which is about the slowest part of the system. So, one is that every iteration loads the data. So that's that. Then you're redundantly saving the output, right, in between every stage. Okay? And so if you think about it, this is what you're trying to do, right? You apply map, you reduce, you do that through the disk, you read more data in, you write that out to disk, and so on. And so if you think about this for not very long, you realize that, well, what you want to do is basically read stuff into memory once, okay? So you don't have to repeatedly read it from the disk. And the second thing you'd like to do is stop communicating through the disk drive, right? So you'd like to do that sharing between different stages of the program, okay? And so this is basically what Spark does, is it takes the map reduce paradigm, and it's smart, and it's basically smart about when you cache things in memory, and that you can tell different stages of the program to look in memory for data rather than having to read it from the file system every time. Okay, so it sounds like a simple idea, and it really was, which is partly why it took off. Okay, and what you end up with is, well, here's the result. So, if you run Hadoop, basically this is how long it takes to do one iteration, that's the blue. If you want to do 10 iterations, it's about basically 10 times that. If you want to do 20 iterations, it's about 20 times the cost of a single iteration, and so on. Whereas with Spark, you pay a price to read things in at first, okay, but then the incremental cost for every subsequent iteration doesn't have the I/O cost, and so you're just doing the computation. And in this case, computation was really, really simple. Okay, and in a lot of machine learning algorithms, the computations are fairly simple. You're just doing it over a lot of data. And so on applications like this, you can get speed-ups of 10 or 100 times over the Hadoop MapReduces, which is what people were using before. Okay? There's also advantages if you're trying to run queries on the system. You read the data in once, and then all the queries can access the data in memory. Seems if you're a database person, it's like, well, how else would you do it? But if you look at the SQL processors that run on top of Hadoop, they read the data in for every query. It just doesn't make sense. So, so that's kind of the big idea in Spark. And then you might be thinking, well, geez, that was easy. So, what's kind of the intellectual contribution? Why did Matej Zaharia, the student who did this work, why did he get a PhD for this? It's a reasonable question. And the reason is because what Matej figured out was really actually quite beautiful. And he came up with an abstraction that underlies Spark called Resilient Distributed Data Sets, or RDDs. And RDDs have a couple interesting properties. One is that they're immutable. Okay, so when you create an RDD, you can't change it. Okay? The second thing is that there's a set of, all you can do to an RDD is basically transform it into a new RDD. So there's basically a library of transformations that say, given some input RDD, apply the transformation, get an output RDD. Okay? And so that's the abstraction. And then, underneath that abstraction is all the mechanism to figure out when the RDD is too big to fit on a single machine, how do you spread it across all the machines in the cluster? And how do you keep track of the different processing that's going on the different machines? Okay? So the amazing thing, though, is this simple model, right? Sets of data that are distributed across a cluster that you can't change, and then a fixed set of coarse-grained transformations that take you from one of these collections to another collection, right? That simple interface, right, that very narrow interface, was sufficient to implement all those models that I showed you on the previous slide. So you could do graphs, you could do SQL, you could do streaming, right? You could do machine learning, right? That's what was beautiful about it, is he came up with sort of the simplest set of abstractions, the narrowest interface you could come up with, and still implement all those things efficiently. All right, and so that's what sits at the heart of the Spark system. Now, when I talk about generalizing MapReduce, this is what I mean. These are a subset of the operators that you can run on an RDD. So the first thing you can do to an RDD is you can run map on it. So you can apply a function to every individual item in the RDD. Another thing you can do is you can run reduce on it. So you could take groups of those things and combine them. Okay? So already we can do map reduce. Okay, so now everything else is just a bonus, right? So if you look here, if you're a database person like myself, you'll get excited because you'll see joins and sorts and group bys and filters, right? So clearly we're going to be able to implement SQL on this thing, right? And then there's a bunch of other things that have to do with flattening data, treating it as a list or not, and so on, partitioning it, and so on. So, this is the language that you have in Spark to manipulate the data. Okay, so why does this matter? Okay, why did you need this RDD abstraction at all? Well, okay, so, when I talked about Hadoop MapReduce, I basically said the problem is it's using the disk constantly, right? It's writing intermediate results out to disk, it's reading them back in, writing them back out again, and why is it doing that? Well, you have to think back to the design point that the Hadoop MapReduce was aimed at. The idea was that you wanted to build sort of an infinitely scalable computing cluster. And you wanted to do it in a way where you weren't particularly careful about what kind of machines you were using, right? So if you're running a big web company or maybe a small web company, you get a bunch of machines, okay, and now your business grows, so you get another bunch of machines, and now your business grows again, you get another bunch of machines. You want to be able to just grab any hardware you could find and bring it into the system. Now the problem is, if you have a bunch of machines all running at the same time, and they're not the world's best machines, or maybe you're not taking care of them as well as you should, and you're running long computations on them, chances are, at any point in your computation, some percentage of your cluster is going to be crashed, right? It's going to be broken. So you need to be able to build a system that's resilient to crashes that are happening in the middle of a computation. Now, in the database world where I come from, we had a pretty simple solution to that. If you're running a query and the system crashes, you just restart the query, okay? But if you're guaranteed that at some point in your computation something's going to crash, that approach gets you nowhere, okay? Because you'll restart, something else will break. You restart, something else will break. And so what the designers of Hadoop MapReduce figured out was that if you checkpoint things out to the disk enough, that if any machine fails, you'll be able to pick up some data, the piece of data that you would have lost, and then just recover that little piece of data and keep going. So you can always make forward progress. So the thing that we had to do in Spark to be able to use memory the way we do is to do it in a way that doesn't break the fault tolerance of MapReduce. And so that's what RDDs do. Because you can't change one, okay, once you've created an RDD, you know what it looks like. And then you have a limited alphabet, you have a limited language to transform those RDDs. So at any point in a computation, you can basically look at a piece of an RDD and know very efficiently where that thing came from, right? So it's called lineage. So here's an example. You have some file in, say, an HDFS that you read. you apply a filter to it. So let's say it's a log file. You just keep the lines that have the word error in them, okay? And then you pull out, I think this is pulling out the third column of each of those lines, right? So you read the file, you filter it, you pull out one of the columns, okay? That's the statement in Spark to do that. Oh, sorry, it'd be nice if I hit the right button. What that ends up looking like, it says, okay, I started off with this file in the Hadoop file system. I applied this filter function to that, and then I applied this map function split to the result of the filter. And that's it, that's the lineage. That tells me for any step in this computation how I got there, okay? So it's very easy during the course of the execution to keep track of the lineage. It basically costs nothing. And then if any machine fails, all you have to know is which part of which RDD you lost, and then you've got the recipe to recreate it, even if you have to go back to the original file. And then if you're smart, you'll do things like checkpointing and some things along the way so that you don't have to go all the way back to the beginning. But that was sort of the key insight to Spark, was that if you make the interface simple enough, okay, two things can happen. One is you can get fault tolerance even though you're doing everything in memory. And two, you can still implement all these advanced functions, right? All these advanced systems. So that is really at the heart of Spark. That's really, and by the way, you can be 10 or 100 times faster than what people were using before. So you put all that together, it's not surprising that a lot of people are interested in that system. Okay, the other thing you could do, and I'm sorry, it's a little bit of an eye chart, but what this is letting you do is, remember, a big part of what we wanted was a unified system. And so what this is showing is, this is doing an iterative computation, a logistical regression. This is a SQL query that returns an RDD, right? That's the core unit of processing in Spark. So we get this user's RDD, and then we can basically, so there's a SQL query, okay? And basically, we can then take the results of that SQL query, treat it as an RDD, and then run other Spark jobs on it, including our machine learning library that we've got. So, basically what the system lets you do is move back and forth from, Scala, which is the native language of Spark, to SQL, to this graph language we have, to the streaming implementation and so on. Okay, so that's what it looks like if you're a programmer. Okay, so I showed you a little bit about SQL. I didn't go into the details. We talked a lot about Spark. I just want to say a couple other things that are in the stack. One is we have kind of a simple approach to doing streaming. So stream processing is basically where you take data, you try to process it as it's coming in. Now, in its purest form, what you want to do is, as each new item comes in, you want to kind of run it through your processing and update whatever results you have. That turns out to be a little hard to do, although you can do it. That was anyway, it's a longer story. But you can approximate that by taking a batch system like Spark, okay, and then shrinking the batch size. Okay, so if your batch of data is a day long, right, then that's how fast your system goes, right? The fastest you can get an answer is at the end of the day, right? But if you shrink that down to an hour, to a minute, to a second, to less than a second, you can start getting an approximation to that kind of real-time processing that for most applications is going to be sufficient. So that was the approach we took in Spark Streaming. It's not the pure approach, but it's something that gets you close for a lot of the things that people were trying to do real-time processing on. And so, the way that works is you take an incoming RDD and you basically chop it into this thing called a D stream, which is basically the RDD from time, from one time period, followed by another RDD, which is the next time period, followed by another RDD, which is the next time period, and so on. So you basically chop the stream into the incoming data into individual pieces. Okay, and then you can apply window operations to it. So if your fundamental unit is chopping your stream into second long intervals, then you can basically do windowing. So you can basically do anything. You can treat that stream as any granularity larger than that fundamental granularity you have. So if you wanted to look at things in 3-second intervals, you would just apply 3-second window operations on it. Okay? And so this is another system that's sitting on top of Spark that is basically just letting you approximate real-time processing using the same exact programming model that you'd use if you were doing batch processing. So I don't think I have the R chart here, but if you look at if you look at a Spark program to process an entire batch, and you look at what the streaming version of it looks like, it's almost identical code. You can actually cut and paste the code from the batch version into the stream version. Okay? So this is another way we can plug in another component of the system. Okay, the last thing I want to talk about in the stack is the way we do graph processing. So here's a problem so let's say you want to do processing in Wikipedia. So you might want to understand the link structure of the operations of the items in Wikipedia. So you have a table of titles and links. You can build that into a graph. You can compute PageRank on that graph, say, and then you can output another table, right, which is like the top 20 most popular pages, right? Or you can follow the discussions. You can build a graph of the relationships between the editors of the different discussions. You can then run a community detection algorithm on it to see who are groups of people that tend to work on similar things. And then you can output that as a table as well. Okay? So this is a typical thing, a typical way that you'd want to do graph processing in a system. And what you'll notice is it's got it's got three kind of fundamental types of structures here. It's got kind of just regular XML files. It's got tables, and it's got graphs. And so we built a system on top of Spark called GraphX that basically lets you view the data using these different lenses. You can view the data as a table. You can view the data as a graph. I've sort of already said this, but the problem, if you do this in a sort of a system that's not our system, you end up having to say, okay, I'm going to use Hadoop or Spark to deal with my tabular data, and then I'm going to use some specialized system to deal with my graph data. Okay? And what we basically said in our project is let's not do that. Let's see, can we build a graph system inside of Spark or on top of Spark that's going to give us all the functionality that you'd get out of Pregel or GraphLab or one of these specialized systems. So we knew we could do that, but then the question is, how fast can you make it go? Right? How much performance do you have to give up from the specialized system to get this more general system, right? Because if it's too slow, it doesn't matter whether you can do it or not, because no one's going to use it. So we built this thing called GraphX, and it basically says I've got a bunch of data. I can view it as a graph. I can view it as a table. Okay? And as good database people, we basically said, we're going to look at these as views in a sense. So we can view the data as tables, or we can impose a graph view on top of it. But underlying it is a common structure. Okay? All right, so we had a paper on this at the last OSDI. But the basic idea is you have a graph, so you've got edges and vertices, and you've got properties. You've got data about edges. You've got data about vertices. And what we do is we say, okay, we're going to store the vertices as a table. Okay? And we're going to have to partition that. So we use this thing that's done in modern graph systems called a vertex cut. Okay? And so we split this across, in this case, 2 machines. And then we're going to split the edges from each partition across 2 machines as well. Okay, so we've got a table that represents the vertices. We've got a table that represents the edges. And then we're going to take another table, and we're going to use that to link these things up. And so what you'll notice is, this says that A has links in partition 1 and 2, and B has links in partition 1 only, and so on. Okay? So we've basically done a tabular encoding of this graph structure. Okay, and using this vertex cut. All right, and so then that's how you do it. Okay, now the question is, how do you make it go fast? So we say, okay, we're going to represent the graph as tables. We're going to represent once we've done that, we can represent our graph algorithms as basically relational operators. Okay? Then comes the fun part. Then you have to make it go fast. And there's a whole bunch of things that we apply, kind of under the covers to make things go faster, including having to implement some specialized join algorithms that weren't in the vanilla version of Spark. Because if you just apply the Spark join to this thing, it runs too slowly. All right. And we're going to materialize a bunch of views in order to make things go faster so that we don't have to keep computing the same thing over and over again. OK, so how does this work? Well, the answer is it works pretty well. So if you try to implement a graph, this is PageRank. If you try to implement PageRank on just Spark, right, you get performance that looks like this, okay, and that's the runtime. So the higher up you are, the worse it is. Okay, and then these two blue ones are two specialized systems, so GraphLab and Giraffe. GraphLab's kind of the one that's viewed as being probably the fastest graph system out there now. And what you see is that GraphX is competitive with these two systems. It's basically usually faster than Giraffe, and sometimes it beats GraphLab and sometimes it loses to GraphLab, but it's within the same ballpark. And it gives you the same order of magnitude speed up that you'd get compared to not having a graph system at all. Okay? So if you look at that OSDI paper, what you see is all the tricks, all the implementation tricks that we implemented to make things run as fast as a native system, basically. All right? But remember, the whole reason we're doing this is because you don't just have graphs, right? You have tables, you have graphs, you have streams. So what happens when you put this thing in a pipeline? So think back to that original example where you're processing Wikipedia pages. All right? Well, if you do all that in Spark, it takes, that's seconds, so 1,500 seconds. Okay? If you do it in a system like Giraffe or GraphLab, well, those systems aren't complete enough to do all the processing. So you have to do your work on the graph system, then you have to move things into Spark, and then you have to process in Spark, and then you have to move it back to the, oh, sorry, I did it the wrong way, sorry. You start in Spark, and then you move it to the graph system, and then you move it back to Spark. Okay? But in our system, it's all in the same system, and you can shrink down that time. You don't have to be copying things around. Okay? So, the amazing thing to us when we did this was we were going to be happy if we could get within a small factor of, we expected to be slower than the specialized systems. And what we found was if we do the right engineering on it, we can actually get rid of any performance problem relative to a specialized system. And then we get the extra advantage of we get to do all the processing in our system, so we can actually go faster on an end-to-end pipeline. Okay? So GraphX is really the system, one of the most recent parts of the system. It's been put into the Apache Spark framework, and it's kind of another proof point. So we talked about SQL, we talked about streaming, now we're doing graph processing, all within this Spark foundation that I told you about. Okay, now at the very top of the stack, we had applications. So I just want to mention this briefly. But we used Spark to implement some genomics processing, and in particular, we built something called Snap, which is an aligner. So if you have a reference genome and you have pieces of some genome, you're trying to figure out what it looks like, you map them, you match them with the reference genome, right? And that's how you line things up. So Snap is a system that runs on Spark, and it basically, at this point, finished an alignment in hours compared to days in the state of the art before. That time's actually come down to like 20 minutes or so. But what's interesting, and this is kind of amazing for us working on system stuff, is the Snap system that we built was actually used by a group at the medical school at University of California, San Francisco, to diagnose a rare disease that this 14-year-old boy had. And what happened was he had brain swelling. They couldn't figure out what it was. They had to put him into a medically induced coma. They took a sample of his spinal fluid, and they sent it to this lab at UCSF that we had been working with. And what they did is they basically ran Snap. They ran a lot of things, but one of the things they did was they ran Snap to basically find all the human DNA in the sample of this kid's spinal fluid and subtract it, and then look to see what they had left. And when they looked at the 0.016% of what was left after they subtracted out all the human stuff, they found this rare infection that was causing his problem. Turns out to have had a pretty simple treatment. They gave him the treatment and he recovered. So, you know, it's kind of a funny, I mean, it's an amazing story, but it's also interesting if you're a student to think, you know, why do I care about big data, right? Why, you know, is that an important problem to work on? I mean, this was an amazing result, you know, you know, work we were doing at such a low systems level was able to, you know, have this kind of real impact in pretty short order. So, so that's kind of an example of what we're doing at the application level. And then what we've really been able to do, and I'm not going to go into it in any detail, but by looking at how people are storing genomics data, so what are the file formats that they're using, basically those file formats were created at a time when the model of computing was, you know, buy the biggest machine that fits on a desk and run it for as long as it'll run, okay? It makes it very hard to spread the data across multiple machines the way we do in a modern big data cluster. And so we came up with our own genomics you know, format for genomics data. And then what that lets us do is spread the computation across a cheap cluster. And what you see is you can start getting, you know, kind of crazy performance speedups of, you know, the traditional genomics processing pipeline, okay, by applying kind of modern big data, you know, best practices to it. Okay, so I kind of took you, I'm sorry if that was a bit too of a long trip, but I took you kind of all the way up the stack. So that's the badass stack, and as you can see, there's you know, obviously a lot of work that's gone into it. And what I want to do is just take a couple minutes, maybe 5 minutes, and talk a little bit about sort of what's the framework. How do you know how can you do this kind of work in an academic setting? Okay, because I think even, you know, we were surprised. Berkeley has a long tradition of building big systems, but we were even surprised at sort of how much we were able to build and how quickly we were able to get it out into the world and really get it used. And it's because things have really changed. And so I think it's an important message, especially for the students in the room, that, you know, it used to be that you could say, hey, you know, I'm just a student, I'm just writing papers, my software doesn't have to work and whatever, and you can still do that. But you don't have to do that. If you really want to have an impact, there's kind of an easy way. It's not easy. I'm sorry, I shouldn't say easy. But there's a way to to possibly do it, and it's through open source software, right? And that's what's really changed. So let's just talk about. I'm sorry, this is all details. It's like, so it's a big group. It's 65 people, and we've got a lot of professors. The main people are, you know, this good-looking guy here and these other good-looking guys. But what's interesting is, for one thing, you probably recognize some of these names depending on what field you're in. But the other thing you'll notice is, you know, we're from a bunch of different areas, right? Databases, machine learning, systems, networks, security, crowdsourcing, right? So we have a group of faculty who do all these different things who decided to work on this project together. And when I say work on it together, I'm not fooling around. So we all share a room that's maybe twice the size of this room. This area here, so these aren't walls, these are desks. And this area here is where 7 or 8 of those faculty sit. So, you know, when you come into the lab, there's professors there, there's students there, there's postdocs there, there's programmers there. You know, that's kind of how you collaborate. And you have to do that because these people all work in different areas, right? If I need to work with somebody in machine learning, I can't just talk to them once a month. I won't know what they're talking about. I have to talk to them pretty much every day. And so that's kind of how we set up the project. The other thing we do that's pretty interesting is from the very beginning, and this is obviously easier to do at Berkeley because we're in Silicon Valley, but it's not impossible to do here. But, you know, we very early started talking to companies and getting companies interested in what we're doing. And in fact, we now have this set of companies that sponsor our work. And Amazon, Google, and SAP all sort of signed up to be major sponsors. And then all these other companies, you know, are involved and sponsor the work and come to our meetings. And so what we do is we meet with them twice a year. All the students present their work. And then we get feedback. each of these companies sends a bunch of people to our meeting, so we have about 150 people there. And the students present their work, and then they get immediate feedback from people in industry who are really trying to solve these problems, who will say things like, hey, that's the best idea I ever heard, or sometimes they'll say, that's the dumbest idea I ever heard. And a lot of times what they say is, well, that was really interesting, but that's not my problem, right? My problem is this other thing. And sometimes we believe them and sometimes we don't, but it's this constant back and forth that kind of makes sure that what we're doing stays relevant to people other than just ourselves. So this is a big part of what we do. So two big things. One is take people from a bunch of different areas, put them together, even in the same room if you have to. And second of all, don't try to hide what you're doing from the industry, but try to bring them in. So we do that. And then we worked really hard to, as we started releasing open source software, we started trying to build a community around it. So it's not enough to just kind of write some software and put it out there. Okay, but you actually have to try to, first of all, you got to make sure it works pretty well. Second of all, when it breaks, which it will, right, because somebody besides you is using it, you got to fix it. And so you have to work with people. And then what you want to do is bring in other people to help you build new things and help you fix it. So now those projects at the bottom of the stack, there's more developers from outside of Berkeley than inside of Berkeley. And in fact, Spark, I believe, has something like 400 developers working on it now. And very few of them are at Berkeley now. But so what we did is we would run meetup groups. This is kind of interesting. I looked and I said, oh, great, we have a Hong Kong meetup group, right? These are all the meetup groups for Spark, but it's not, it's Shenzhen. But it's close. You could just take the train up there and you can go to a meeting about Spark, or you could start one here. So there's a big thing you have to do to kind of build the community and get people excited about what you're doing. But what's fun is if you're a student and you built one of these systems, and I mean, it's not easy to do, but you could be standing up there, and you could have this group of people listening to your every word because they want to use what you've built and learn how it works. And it, if you can get things going, that's what can happen. So yeah, so what's changed? So one thing that's changed is people have figured out that open source software can actually be useful. And in particular, for things like analytics, where maybe it's not a life or death situation, that if the system is down for a little bit, it's not the end of the world. People are willing to try out new software. And in particular, for big data, since the problems are so hard, and the systems that are out there are, in general, not sufficient for the next big problem, people are willing to try anything. And if you put software out there that's at all useful, somebody's going to pick it up. Somebody's going to say, hey, this is great, except this thing didn't work. It'd be nice if you did this. And then that's how you start, that cycle of actually, getting the software to a place where other people want to use it. And so, if you're interested in building software, it's a really nice platform to do it in, right? This whole open source environment. Now, and it doesn't have to be Spark. You don't have to have this brainwave that Matei had. Matei's the student who did Spark. We had a class project. We had 3 students who said, hey, I like to program in R. The problem is R only runs on single node machines. I'd like to be able to run R on a cluster. So what I'll do is I'll write a translator from R into Spark. And they wrote that thing. It was a class project, so they didn't implement the whole language. They implemented some big piece of it. And then, they didn't know what to do with it, so they just put it in the AMPLab GitHub repository. Well, people saw the word Spark, they saw the word R, or the letter R, and they said, wait a minute, that's exactly what I want. I want to be able to run R on Spark. And so people started using it. And the next thing these students knew, they had a whole community. And actually, it was too much for them. They were theory students. They didn't want to be doing it. And so they found other people out in the community to take it over. And so now there's kind of an increasingly full version of R that you can run on Spark that started from a class project. So, and you don't have to be at Berkeley to do that. You could build anything on top of Spark, and if it's useful, somebody's going to try to use it. Okay, I'm going to skip that. I just want to mention, for the professors in the room, you might be thinking, well, that's great, but unfortunately, I have to do research. These are the 8 students who've graduated from our lab in the last 2 years. So a lot of our students go to industry, no question about it. But of these, 3 are now professors at MIT. One's a professor at Stanford. We get papers published, so So you can do research and get the software out. Okay, last thing I want to talk about. Do I have a minute? Okay. So last thing I just wanted, so that was a little bit about sort of the culture that we've tried to create to do this type of research. Okay, and I should mention, by the way, if you're interested in that, there's a paper that one of the lab members, Dave Patterson, wrote in the CACM, I think in March of this year. It's called How to Build a Bad Research Center. And that's where it goes through a lot of sort of these rules about getting people together and how to do that and so on. So if you're interested, it's March 2014 CACM. All right, so the last thing I want to talk about is sort of this idea of big. So at the beginning, I talked about what's big data and sort of did I admit, not a complete definition of it, but try to get you thinking about, how I like to think about big data at least. Think about it as an opportunity, not a problem. Okay, and it's not about how many bytes there are. But what about the underlying ecosystem, right? I've been working in data management for longer than I care to admit, and the question is this just the next turn of the crank? Is this just the same old thing, right? I've done caching, I've done query optimization. Is that what's going on here? And the answer is, well, of course, right? I mean, yes. I mean, there's fundamental things about building systems that aren't going to change. Memory is faster than disk usually, right? An optimized query is faster than an unoptimized query, right? Algebraic approaches allow you to do optimization. These things are of course, not going to change. But, has anything changed? And I argue, yeah, that things have actually changed pretty fundamentally. So I kind of want to talk about that just for a minute. All right. So lots of people have tried to do this kind of integration, right? So I worked for a long time on streaming SQL systems, right? There were these things called object relational databases, right? Extensible database systems. So lots of people have tried to build sort of general systems that let you, do programming and queries and streaming and so on. So, so what's really fundamentally different here, right? This is all work from 10 or 20 years ago. Okay, well, I do think it's different. And here's the thing, is that, when you think about big data, you think about scalability. Okay, but that's not really what's going on here. We've known how to build parallel database systems for a long time. All right, so it's not really about scalability. It's not really about speed either. We've known, like I said, we know how to optimize queries. We know structures that make things run faster. Okay, so that's not it either. What's fundamentally changed from a database perspective is flexibility, right? So the big data ecosystem is incredibly flexible, okay, in a way that database systems never were. So I just want to talk about that just for a second. So here's the traditional way that it would work, right? You'd have if you wanted to do analytics, you'd have some data source, whether it's logs or some documents or some database out there. And you want to get it into this thing called a data warehouse, so you get all your data together and then you can run analytics on it. And the thing you do to that is a process that if you live in this world, you know about, and if you don't live in this world, you probably never thought about, but it's called ETL, extract, transform, load. So take the data out of where it was, change its format so it can go into the database, and then put it into the database, extract, transform, load, okay? And this is kind of the fundamental place where systems slow down, okay? Because it's expensive, it's hard to do the mapping, there's a lot of reasons why that's hard to do. Okay, so what's different now? Okay, well, the reason that you had to do that ETL was because databases store structured data, okay? So if you want to create a data warehouse, it's very simple. Figure out what every single piece of data you're ever going to collect looks like, code that up into an SQL schema, and then load that schema in your data warehouse. And then, if you haven't been fired or your company hasn't gone out of business, by the time you've done all that, you could start figuring out how to extract and transform the data to get it into that database, right? So step number one is describe the data exactly how it's going to look, okay? And hope it doesn't change after you've done that, okay? So that's how databases work. On the other hand, on the other side of this thing, you can just say, no, I'm just going to throw everything into the file system, and then all I can do is basically run grep on it or something, right? And then there's a trade-off here. On the structured side, you have a lot of control over what your data looks like, and because you know what it looks like, you can compile the access to it, so you can read it really quickly. Over here, it's kind of the opposite. Since you don't have to transform the data or worry about what it looks like, all you have to do is store it. It's really about as fast as you can load it. But, and you can kind of put anything in there. But the problem is, there's no guarantee when you try to get data out of there that it's going to be what you were expecting. Okay? And then there's this middle ground called semi-structured. Okay? But the key point is that in the past, if you wanted to do analytics, you had to be on this side of the world, or maybe in the semi-structured side of the world. But you couldn't do analytics over here. You couldn't run, graph algorithms and queries and things like that over here. Okay? And what's changed in the big data space, in the big data ecosystem, is that now, and I hope I have this, is that now you can actually live on that right side of that chart. Okay, so you can basically just take all the data and just store it. And then when you actually want to process it, that's when you impose the structure. So sometimes it's called schema on read. Okay? And so the other word for this, people have been using a term called data lake, which is kind of a weird term. But you just put all your data in there and then you kind of pull stuff out when you need it. So one big change that's happened with big data infrastructure is you can now do analytics over loosely structured data, right? And so that's huge because, remember at the very beginning of the talk, I talked about where all this data was coming from everywhere. And if you had to figure out the schema of all those different applications, you'd never be able to do it, okay? But now you just store the data, and then the trick is that when you want to access the information, you pull it out, you apply the structure to it then. Okay? And there's challenges with that. It's not a completely solved problem. Okay? And in fact, a lot of guarantees that we used to like to give in database systems, you can't really give anymore. Okay, but that's fundamental. That's different, right? You can run queries on unstructured data. The other thing, which is pretty similar in flavor, it's about flexibility, is this is the way it used to work. If you wanted to store your data in the database, you made a deal. You said, okay, database, here's my data. The database would take the data, it would convert it into some format that you never knew what it looked like, and then you basically had one way to get at it, which was you could write a SQL query. So the data goes in the database. If you want to get it out, you write a SQL query. Okay? And the promise that the system made was, okay, I'll guarantee certain types of consistency and so on. Okay? But if you look at how the big data stack looks, it's not like that at all. Right? Remember when I showed you the badass stack? It's all these different layers. And you can get at the data through any of those different layers. So in the old days, there was one way in and one way out. Now, if you want to run queries, you can. If you want to treat the thing as a graph, you can. If you want to run a MapReduce job on it, you can do that. If you want to just put the data and get the data, you can do that. And so all the data is sitting there in this storage mechanism, and then you have all these different ways of getting at it. Okay? So again, a lot of the barriers that had been put up by the traditional database systems to people who wanted to do analytics or big data processing are now gone. Okay? But there's huge challenges. How do you get the guarantees that you used to have? How do you get the performance that you used to have? Right? People are starting to work on these things, but there's a lot more that has to be done. But if you ask me what's different now than say from when we were doing scalable databases 10 years ago, it's that flexibility that's different. All right, so there's a bunch of open research problems. I think, if you're interested, we could talk about them later. Just to summarize, and our approach in the stack was to kind of unify things, not specialize them, but try to bring it all together. And there's a lot of interesting engineering and research that you have to do to get the performance out of that system. I spent some time talking about the research environment that we've built in the AMPLab, and it has to do with getting people from different areas, making sure you engage with industry because they're the ones that are seeing a lot of the problems, and then leveraging open source to get your stuff out there and to get people to help you build it. And then try to make the point that there is something fundamentally different about this new class of systems compared to the way people were doing analytics before. Okay, so I'm done. So, sorry. the main point. You know, the way the world's set up, you can be working on your PhD or your master's or whatever, and you can participate. Okay, so there's lots of companies out there. There's a lot of activity, but because of the way this space works, especially with open source software and people willing to try things, you can be working on your research and be participating in this environment as well. And so that was really kind of, if anything, if you remember anything from the talk, that's kind of the main point. All right, so now I'm really done. So thanks for your patience.
Okay. So any questions?
Yeah, so the question was what's in the machine learning ML base? Yeah, I already talked longer than I was supposed to, so I didn't go through all the parts of the stack. But ML base is really two components. There's a library of machine learning functions that just implements various clustering, recommendation systems, topic analysis, and things like that. And then ML base is a layer that sits on top of that that tries to do the analogy is the same way a database system takes a query written in a high-level language and compiles it into something that runs on a set of join operators and things like that. We're trying to do the same thing. So you specify the machine learning with some sort of high-level language that we're still designing, and then that gets compiled into a program that runs efficiently using the operations that are in the MLlib. And so MLlib is out there, and you can use it. It's similar if you're familiar with Mahout, which is a machine learning library that runs on Hadoop. MLlib is kind of like that for Spark, except that Mahout decided to move to Spark too, so it's a little weird. ML base we're still working on. We have a paper on the optimizer if you're interested in seeing that, but we're still building that one out. There's a question here.
Mine's are probably more specific. I know some of the people on the student slide.
Okay.
What type of things did you do with Tamara and John Ducci?
Oh, okay. So yeah, two of the pictures I showed of students up there. So actually, Tamara's going to MIT and John's going to Stanford. John did a bunch of work on he did a bunch of work. So he did a bunch of work on privacy that we're interested in incorporating. He also did a bunch of work on asynchronous algorithms for computing various things. And so the Velox project that I didn't talk about, part of what's in there is the problem with Spark. The problem with Spark is it works using this model called bulk synchronous processing. So every iteration finishes before the next one starts, and what we want to do is relax that constraint, so to be able to do asynchronous processing. And that's been known to work for certain things. John figured out some things that it works for, but we're trying to figure that into the system. And Tamara's stuff, honestly, was not in the core of the system, but I think some of it is getting into MLlib. But I didn't focus on all that work.
You're not doing anything like variational Bayes?
I don't know if the variational Bayes is going in MLlib or not. Yeah. But if you think it should be, you should tell her.
Your view, what's the difference in relationship between data science and big data?
Oh, wow. Okay. How much time do you have? No, actually, so good. So what's the difference between big data and data science? I thought I had an answer to that, because it certainly comes up a lot. So I think I teach a class in data science, and the first 3/4 of that class, everything we do is on a laptop using Python, on data that's maybe megabytes, maybe a gigabyte. So that's not really anyone's definition of big data. But yet, there's still a lot of, thinking you have to do to be able to, if somebody hands you a gigabyte of data and says, find something interesting in there, that's hard to do, and no one's going to call that big data. So I feel like, data science is kind of a bigger concept, and sometimes you do data science on big data, and sometimes you do it on smaller data sets. And yeah, I mean, the other way to think about it is I feel that big data is kind of more of an industry term, and data science is maybe more of a new field of study. So that's not a good answer either. So in general, I've been asked to review a bunch of. So there was one school that was putting together a new master's program for this stuff, and they called it the Masters in Big Data Science. And I said, drop the big, So I guess I feel like data science is more of a discipline, and big data is a little more of a marketing term.
How do you think this can help to improve processes in normal companies?
What's a normal company?
Well, there are
I've
a lot
never
of
seen
companies
one.
have processes where they store data,
Uh-huh.
but they don't know what to do with the data. So how do you think we can use this to improve those processes?
Yeah, so, I painted this really nice picture of this world where everything's flexible and, you don't have to worry about the schema. You just take the data and you store it, and then when you read it out, you figure out what it looks like. And, if anyone here has, owns a bank, don't do that. Don't do that for the accounts, at least. You can do it for the log data, and you can do it for, other things you can do an analysis on. But if you're managing my bank account, don't do it that way. So I think the answer is that what this lets you do is it lets you explore the data more. It lets you look at more data and explore it. So there will always be kind of transactional applications that you need more guarantees for. But for a lot of analytics, I think the guarantees that you're going to get are going to be statistical anyway. And so as long as you can provide some statistical guarantees, you get to look at a lot more data. So I think I'm not sure I'm answering your question, but I think there are certain business processes that this won't affect at all. But what it's going to let you do is new business processes that are based on things that you learn from looking at trends over large populations. And so I think it's going to be kind of new functionality, not replacement of old functionality. Is that?
Spark is great. It's efficient and scalable, easy to use. But my question may be a little bit tough. What kind of problem that is Spark is bad at? That is very hard for Spark to process.
Oh. I knew there was. I'm trying to remember what it was. There was one. No, actually. So that's a perfectly good question. So what's Spark bad at? So, well, Spark is bad at anything that requires you to do point updates or point access. So anything where you need to go in and change one little piece, so you've got this huge data set and you've got to change one little piece of it. You don't want to do that with Spark. That's why we're building this system called Velox. So Spark is meant for kind of batch or stream processing, input and output. And so anything where you're going, kind of, sometimes it's called rifle shot. You're just going right for data, and you're either retrieving it or updating it. That's one thing. And then the other question that comes up, which I think is a really good one, is, when do I need a cluster, right? If I just bought a big machine with a lot of memory, right? Because memory sizes are growing. And there's a bunch of problems for which the data isn't growing that fast anymore. When do I need this kind of massively scalable system? And so I think there's an interesting question about, are there workloads that I know for sure are always going to fit on one machine? And maybe Spark's not the best engine for that. So those are a couple that come to mind. I'm sure if you ask people at certain companies, they would have other ones. Companies that compete with Spark.
One more.
I can imagine that the next Congress is going to say, let Google and Apple and all the rest of the people do it. Let's cut off the seed money for such programs. What's going to happen? How crucial was that for you? What's going to happen if that happens?
Yeah, well, so it's an important question for sure. When we started the project, actually, if you look at this article I mentioned that Dave Patterson wrote about building these research labs like this, that model was actually started in sort of one of those periods where the federal government had backed off of funding research in computer science, and what they were able to do there was to get companies to sponsor the work. So that's where this model of building a consortium of companies comes from. And when we started our project, our initial plan was to just do it with industry funding. And we were just sort of pleasantly surprised that the government got interested in funding what we were planning to do anyway. And so our original plan was to build a project that was about half the size of the one that we built. Since we were able to get government support, we were able to build this much bigger project. And I think realistically, it's that combination. If it was just government money, there's a bunch of things that we did here that we wouldn't have been able to do, like hire programmers and people like that. On the other hand, if it was just the industry money, we wouldn't have been able to scale, horizontally and vertically the way we scaled, to do the whole stack. And so, we just had a midway review from the National Science Foundation, and we had this discussion with them we basically said that without the funding we got from you guys, we probably wouldn't have been able to do half of what we've done. So it's it's a problem, but I think, well, I don't know. I guess I'm a little more optimistic than that. I'm not. I think there's a bunch of projects that have been able to show the benefit of this kind of research. So I don't know. I don't have a good answer. But I guess the thing I will say is that at least in our we were able to get companies to step up to bridge part of that gap at least.